Hey guys, this is the recording for the second electrical workshop in which we'll be making our schematic. So let's start off by creating our project. Just click new project and then probably make a folder on your computer. I made a folder in my documents folder under KiCad projects. Let's call this one Precharge. I cannot spell Precharge video. So as you create the project, you'll see two files over here, and we would like to open the schematic to edit it. So let's go ahead and open it. So this is our schematic sheet, and we'll need to make it. So essentially, we'll be implementing this circuit that I've simulated over an LT-Spice. Zoom into it. So we'll have a couple of resistors, a Zener diode, a timing circuit, and then MOSFETs, as well as two connectors on both sides, as well as a miscellaneous connector for switches. So let's start off by placing our first components, which will be resistors. So we go under add symbols A and type in resistor. Uh, because we're in Canada and we're greatly influenced by US, we'll be using the US symbols as is the standard here. Okay, cool. So we placed our first resistor. Um, if we refer back to the simulation, we need two 1 mega ohm resistors, one 10 kilo ohm resistor, one 1 kilo ohm resistor, and one 100 ohm resistor. So let's start off by configuring this one to be 1 mega ohm. By right clicking and clicking on properties, we can pull up this window, and here we'd like to change the value to 1 mega ohm, and then we would also like to change our footprint to 0603 for resistors 0603 1608 metric. You can also show this. We don't exactly require a datasheet for this one, and we're not too concerned about how much power this resistor is gonna draw, so we don't exactly need to populate those fields. This is pretty much it for making a resistor with a already known footprint. Okay, maybe let's, instead of showing the footprint, I think it would be better if we included the footprint size in the value, which makes it much more readable. Alright, because we need two of these, we can select it, press Ctrl C, and then Ctrl V to copy it. Okay, so all of our visitors will be of 0603 package size, and only the value will change. So we can go ahead and copy these guys over. So we need R3, which will be 10K. We'll need R4, which is 100 ohms. And we'll need a 1 kilo ohm resistor. Cool. Now, we would also like to have a capacitor for our timing circuit, which, let me bring it up real quickly. So right now we placed these four and this resistor. Now let's plop down this capacitor. So let's go back into the symbols, type in capacitor. It will not be polarized for our own convenience. So let's go ahead and plop this one down. This one down. Cool. We'd also like for it to use the 0603 package. So go ahead to footprint, type in 0603, and it should be under capacitor SMD. So capacitor 0603, 1608 metric. So that's exactly what we want. So let's select it. Cool. Under value, 1 microfarad RE. There's also an additional consideration with capacitors because they have a voltage rating and a noise rating, noise slash voltage response. So there's two ratings that would fit our purpose, which are X5R and X7R. Let's quickly take a look at what the difference is. So as temperature increases, the capacitance of the SMD capacitor would change a lot. X5R and X7R are not affected by changing temperature that much. Therefore, they're pretty good for our application. I guess I should zoom in. Go. Yeah, as you can see, the Y5V and Z5U have a huge spike at the room ambient temperature, but they get pretty derated as soon as we exit favorable conditions. Finally, we want to specify maximum voltage that can be handled by the capacitor, which in our case is about 60 volts. Assuming a 42 volt source. Cool. So let's flip this one by selecting it and pressing R. Now we just need to add a handful more components, starting off with transistors. So let's go ahead and choose a new symbol. It'll be an NMOS. They give us quite a lot of options, but none of these would necessarily fit our needs. So instead, let's select generic NMOS transistor and configure it to our needs. So firstly, we are going to be using the IRFS 7530 because we have quite a lot of them and they are suitable for this application because of their VDS, which is the drain to source voltage. So if we go into DigiKey or Mouser, both which are reputable electronic component distributors, and type in IRFS 7530, we'll get a selection of them. So we specifically will be going for the 7ppbF. Let's open up the datasheet to document what we need to implement on the schematic. So, like, pretty much straight on, we can see that it has 7 pins in total. One of them is the drain, 5 of them are sources, and one of them is the gate. Also, we can see that it uses a pretty common package type, which is also specified over here. One, please. Yeah. TO263-7. All right, so let's go back to our schematic and find the footprint. So we'd like to have a TO263 6 in our case because we are missing the middle pin. Right. And let's enter the name of our MOSFET for the value. We could also change the datasheet to reflect what we're like the datasheet will be using, the MOSFET will be using, which makes it easier for verifying your schematic and just debugging once the board is done. Cool. We could also alter the description. This one works just fine. And channel 60 volts, 240 amp, surface mount transistor. Okay. As you might have noticed, the amount of pins does not match. So to fix that, you might want to change the pin functions. To do that, we'll have to go into symbol editor and symbol editor from the MOSFET. Edit symbol. There we go. So from here, we can go into pin table for pin assignment and add the extra 4 source pins. So if we go back and look at the DigiKey website and go back to the datasheet, we'll see that our drain is on the big pin and our gate is on the leftmost pin. If we were to verify this with our footprint, 4 is this big tab, and this is pin 1. So effectively, we'd like to add more pins such that pin 1 is our gate pin, our drain is pin 4, and the rest, so 2, 3, 5, 6, 7, double check, we have 7 in total. Yes, 7. So this makes it so that the source has pins 2, 3, 5, 6, and 7 assigned to it, and whereas drain has pin number 4 and gate has pin number 1. So I'll click OK and save it. It will match. You can double check the number of pins undergoing under pin functions. Alright, slight correction. I forgot that we also need to modify the amount of pins. So if we go back to edit the symbol and go under pin table, we need to change the count to be 5. And if we group them by name, we'll get our appropriate count. Okay, I might have added way too many. I just copied the source pins using Control-C and Control-V. Cool. So now, if we group them by name, we'll see that we have 5 pins under source. Let's reassign the numbers once again. So it'll be 2, 3, 5, 6, and 7. Cool. Now once we save, we can verify that our properties match the number of pins. Great. Now we can take this guy and copy it over 2 more times. Cool. Now we're missing a couple more major components. One of them is the Zener diode. So if we go ahead and place a Zener diode, this one will work just fine. Yeah, once again, rotating by pressing R. We need to find one that suits our needs. So from simulation, we obtained that the value of 12 volts is pretty sufficient. Now, after doing some math, effectively calculating the max current that can be dissipated through the Zener using the rest of the resistors, which is effectively 42 over 10k, which is 10 to the 3. We'll get that our max current is this many amperes, or this many milliamperes. So from this current, and multiplying it by the voltage of the Zener diode to obtain power, we'll get 50 milliwatts. So to just be safe, we can multiply this value by a factor of 33%, extra 33%, and get 70 milliwatts. Cool. Now we just need to find a Zener diode that will work for our application. So if we go in and type in Zener diodes, go on those single Zener diodes, we could find that there's a lot of options. So let's specify our requirements to find an appropriate one. So we can see that the maximum power is way bigger than whatever we calculated, so we don't necessarily need to worry about that. But we definitely need to modify our Zener voltage. 12 volts. Go ahead and select this guy. Let's also make sure that it's in stock. It is not from Marketplace, and it also has a data sheet. Okay, so now if we sort by price and ignore the bulk orders, especially because it's a MELF, which are really hard to solder, you can see this guy, BZT52C12. So let's go ahead and look at what the package for it is. It uses SOD123. So let's go back to KiCad and configure our footprint to be the same as the diode group we're using. So let's select DSOD123, change our value to be a 12 volt, 200 milliwatt SOD123 Zener diode. And add our datasheet. And all the description as well. 12 volt Zener. We'll obtain the diode we wanted. Cool. From here on, we just need to add our power connectors on both sides, as well as our switches, or rather the switch connector, and route everything. So I have provided you with a file, an archive containing the connectors we'll be using. So if you check your Discord or wherever you downloaded them to, and open the archive, called AMSP45 blah 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 blah, you'll see the folder called ASMP blah 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 blah. So let's copy that folder over to our project folder. So let's create a folder for components, and let's copy the new folder in. So now we just need to add it to the schematic. So if we go to symbol editor, we can go into preferences and manage symbol libraries, and then go into project specific libraries to obtain a menu for adding new components. So we'd like to add an existing library to table, and it'll open up our folder with the project. Let's go into the components, ASMP blah blah blah, blah KiCad.sim. So once we press OK, it should generate a new entry in the item. So now if we were to add a symbol and type in ASMP45 blah 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 blah, it would give us this component. Now let's note that this component doesn't yet have a footprint, which we would like to add to it. So let's go into simple component footprint editor, go into preferences, manage footprint libraries, go under project specific libraries and add an existing one. If you go under components, ASM blah 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 blah, and select the folder, we'll get our footprint. So if we were to now open the properties and make sure that our footprint is ASM 45 blah 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 blah, it will effectively work. We can also add a datasheet for this guy because datasheets are nice. So let's go into DigiKey, type in this code, I'll open up the connector. We can copy the datasheet over to the appropriate field. We can add a description. And that would be pretty much it. Also note that the first pin would be a ground pin, and the second pin will be a positive power pin, which we might need to look out for. At the end of the day, we can technically reassemble and assemble this connector however we please, so it's not a huge deal, but it's nice to be consistent. So in order to do that consistently, we said that pin 2 will be red, and usually by convention schematics flow from top to bottom, left to right in terms of power and signal delivery. So we'd like to have our pin 2 on top. So let's select the symbol and reflect it vertically. Now pin 2 is on top, and we're good. Let's take a copy of it for our output and reflect it along this axis by pressing mirror horizontally. Sorry. Cool. Now we just need to add our connector for the button. So let's go. We know that it will need to have 5 pins. So there's a generic connector with 5 pins. Connector 0105. I really like this one. because of the way it looks. Let's assign a footprint to it. Let's go with a JST PH. $2mm connector. I prefer to use vertical connector for this for no strong reason. We can also add a datasheet if we search up a JST PH over here under headers. And specify 5 pins. We got quite a number of them, but this one would probably be the best fit. So if we use a datasheet, also update value and add a description. We'll be done editing this symbol. Cool. Now we just need an LED for the output voltage, for the output indicator, and we will not be putting one onto the schematic, but we'll need to make sure that we have appropriate connections so that we could connect it. So in order to not burn down the LED, we need to put a power limiting resistor. So let's go ahead and copy one of these over. But one thing about it is that we don't know what the value of it is because we don't know what LED we're going to be using. So let's say that will be our LED, and we will not populate it, as well as excluding it from the bill of materials. Alright, so now we just need to route our schematic, as well as adding a few nets. So labels in KiCad essentially connect two wires, even if they're not connected on the schematic. Here's an example. If I have these two wires and I put the same label on them, let's call it label A. Both of these wires will be treated as the same wire for when we make the PCB from the schematic. So effectively, labels as well as power symbols allow us to connect nets without much hassle and without having wires stretch across the whole schematic. So let's start off by plopping our power symbols down. We have battery, positive battery, negative battery, for this connector, J1. We won't be putting a fuse for this revision of the pre-charge boards. So our positive voltage goes straight to the output, but our ground becomes negative output voltage. So let's take some symbol. Let's go ahead with this one. We can rename it to whatever we want so that it goes on a new link, on a new net. So let's call it negative V out. we were to rotate it and put it on the output, it will be golden. Cool. So I still need a few nets over here. So one of them will be named NO for normally open. One of them will be named switch for the middle pin of the switch. And one of them will be named NC for normally closed to signify the two positions that the switch can switch to. Finally, we'll have an LED plus and LED minus, which are effectively V out and the battery connected through a resistor. So let's go ahead and add those labels. So as I said, negative V out for the LED output, positive LED number 4, normally connected for pin number 3, switch for number 2, and normally open for pin number 1. So the challenge is to now route the rest of this schematic using these net labels and wires. I suggest that you try to do it yourself before you take a look at me doing it, and you could refer back to the simulation to help you. Right, so feel free to pause on this slide or this frame and unpause whenever you're ready to check your work. Right, so we know that all the resistors, all 1 mega ohm resistors form a voltage divider between positive voltage of the battery and the negative voltage of the battery. So we can go ahead and place plus VBAT and negative VBAT to form our voltage divider. Then we know that the middle will be connected to the switch. Go ahead and copy this label over. Now we also know that these two resistors will also connect to negative V battery, positive V battery, and then to the corresponding NC and NO. Okay, so by default we should be off, so our NC should go to 100 ohm connected to the battery, negative of the battery, whereas this should be the on position. Okay. Let's just make it slightly more beautiful. Cool. So now we can place our Zener diode. It needs to be connected to the switch as well as the negative of the battery. All of the gates of the MOSFETs will be connected to the switch. Perhaps there's a better way to connect them. Then the sources must be connected to ground. Note that the wires don't, even though they intersect here, they are not connected because you do not see the dot. So this is a pretty important part of reading a schematic. Now we need to add our timing circuit. So the resistor will be connected to the diode, and the capacitor will be connected to the drain. Also, all drains of the transistors need to be connected. Let's shift this section down slightly. So using labels allows us to declutter the board, the schematic quite a lot. So I do recommend using them. Now we also need to put down our LED, which will be connected between the positive voltage for the battery and the positive output, the LED. Now the only thing we have left is to place the Vout label, negative Vout label, which effectively will be our drain. Okay, so if we do a bit of reorganization, you'll get our final schematic. So this is pretty much it. Thanks for watching the video, and see you next time.